We are going to combine section 7.5 with section 7.6. And in section 7.5, we're only going to be covering the powering property. But before we jump into there, I want to review with you from 7.4, when we are solving equations with logs, we were able to take a log that was on both sides, and as long as their bases were the same, we could set the rest of it equal. The reason why we were able to do that was because the log was alone on each side. That is no longer the case in 7.5. We have now introduced other numbers in front. So I cannot just set these two parts equal to each other because this 2 in front says that you need to deal with it first. How we're going to deal with that is using the powering property. The powering property indicates that when there is a number in front of a log, we can move it to be the exponent of the number after the log. So this n times log base b of x can be changed to be log base b of x to the nth power. And if it was written this way, we'd be able to write it in reverse as well. So that means for this first problem, and guys, these are the two new problems. They're not already written on your notes. You'll have to write them down. But we can take this 2 that's preventing us from being able to just set the 6 equal to x, and we can make it an exponent to the 6. So I would have log base 2 of 6 squared equals log base 2 of x. Now it looks exactly like a problem that we might have done in 7.4. We have a log with the same base on either side, so I can set the part that comes after it equal to each other. So the bases are the same, so this part can be set equal. 6 squared, which equals 36. Here, that 2 got a little big. I'll just change it to a 36. Equals the x. Let's take a look at the next one here. The 3 in front here. That 3 in front is preventing us from just setting x equal to 8. I need to make that 3 an exponent. So I have log base 2 of x to the 3rd power equals log base 2 of 8. Now I have a log by itself on both sides. The log on the left side doesn't have anything in front, and there's no other logs. Same for the log on the right. So that means I can take and put this x to the 3rd equal to the 8. To get rid of something to the 3rd power, I take the cubed root of both sides, giving me x equals 2. Let's take a look at the last one here. The 3 in front is what is preventing me from actually being able to just set the x equal to 125. So I need to take the 3 and make it an exponent. So I have log base 3 of x cubed equals log base 3 of 125. Now that the bases are the same, and I have the logs alone on either side, I can set these two equal. X cubed equals 125. To get rid of a cube, you cube root. So x is equal to 5. One thing that I want to mention and make sure that you're aware of is that if you were taking a square root, you would have to put a plus or minus, and then you always need to double check that these actually work in the problem. If you ever get the log of a negative number, then you need to make sure that you exclude that number. Let's come up with one other quick example so we can see this in action. So let's do 2 times log base 4 of x equals log base 4 of 16. Okay, so I know that this is a really simple problem for you to be able to do. You can evaluate this side and then translate, but it illustrates the problem that I was trying to show you. That 2 in front is what's preventing me from just setting x equal to 16. I need to take that 2 and move it to be the exponent. So I have x squared log base 4 of x squared equals log base 4 of 16. So now that the logs are alone, I have x squared equals 16. Square root both sides. So x is equal to plus or minus 4. If I take that positive 4 and put it in for x, then I can get that the answer is true. But as soon as I take that negative 4, I now have log base 4 of a negative number. And that doesn't work. So actually, the negative does not apply. The answer is only positive 4. You cannot take the log of a negative number. Let's flip over to 7.6. Work out a couple of problems. 7.6, remember that when we don't have a base written, we assume that that base is really 10. And the beauty is that your calculator can do log base 10 pretty easily. We have log button on our calculator. That does only log base 10. So if I just do log of 5, then I get my answer here, 0.6989, which technically that 9 would round up. And make it 6.99. Same with log 21. Type it into our calculator. Log of 21, 1.3222. Log of 0.4, log 0.7. Same process. Log 0.4, negative 3.97. Sorry, negative 0.3979. And then log of 0.7. You are only able to do this if you have log with base 10. So log of 0.7 gives me negative 0.1549. Log of base 10s are fantastic because I can use my calculator on them. And that's actually how we will solve the problems that look like this. If you think back to 7.2, 7.2, when we saw problems that looked like this, we tried to write them with a common base. For example, if I had a 6 over here and a 36 over here, I could write the 36 as 6 squared. But I'm not able to do that with 6 and 40. No matter what base I use, I would never be able to raise the same base to a power and get 6 and 40. So we have to figure out other ways to complete problems like this. We do that by taking the log of both sides or using that base 10. If I take the log of 6 to the x and the log of 40, I can now use the process that I was using on my calculator and use our power property from 7.5 to solve this problem. The power property says that that x, because it's an exponent, gets to be moved in front. So I have x times log of 6, log of 40. And this is really x times log of 6. So if I want to get x by itself, I just need to divide by log of 6 on both sides. So on my calculator, I'm going to type log of 40, close my parentheses, divided by log of 6, close my parentheses. So x is equal to, and it wants us to round it to the nearest 10,000th, 2.0588. Let's take a look at the next one. I can't find a common base for any of these problems. So my first step is going to be to take the log of both sides. So I have log of 2.1 to the a plus 2 equals log of 8.25. That a plus 2 can become the number in front, the coefficient of the log, because of the powering property. So I have a plus 2 in front. Notice I have it in parentheses. That is very important because this whole a plus 2 is multiplied by the log. If I don't put parentheses around it, then I would only have the 2 multiplied by the log. So if I want to get this a by itself, I need to divide both sides by the log of 2.1. So I have log of 8.25, close your parentheses, divided by log of 2.1, close your parentheses. And I get the a plus 2 is equal to 2.8442. Now notice I'm keeping that whole thing in my calculator, that whole number in my calculator. And that's because I'm still trying to get a by itself. I have some other operations to do. So I'm going to subtract 2 from both sides. So that means I have this whole long number, subtract 2. And that gives me a equals 0.84412. Sorry, I said that wrong, 0.8442. Let's take a look at C. I need to take the log of both sides because I can't find a common base. That x squared needs to come in front because it's the exponent. So I have x squared times log of 7 equals log of 20.42. In order to get that x squared by itself, I need to divide by log of 7. And that leaves me with x squared equals, on my calculator, log of 20.42, close your parentheses, divided by log of 7, 1.5502. Now I need to get this x by itself, and I do that by square rooting both sides. So we have x equals, and I don't want to just type this number into the calculator because that's a rounded number. I want to use this whole number from my calculator. So I'm going to press second square root and then second answer. Answer is the negative button. So my final answer is 1.2451. Let's take a look at D. In order to solve this, I need to take the log of both sides. So that means I now have two exponents that need to be moved in front. The b minus 3 needs to be moved in front and put in parentheses. B times log of 5 on the other side. Okay, now I don't have a clear path to get a b by itself because there's a b on both sides of the equation. So really and truly, you can choose to divide by either side. If you divide by log of 5, then you'll have a little work to get the b by itself on the other side. If you divide by log of 11, you'll still have to do a little bit of work. My personal suggestion is to always divide by the log that's with any parentheses. If they both had parentheses, you don't really have a choice, but since this is the only side that has the parentheses, that's the one that I'm going to do, because what these logs really represent are long, nasty decimal numbers. And I don't want to have to take that long, nasty decimal number and distribute it across any parentheses if I can avoid it. So the side that has the parentheses is the log that I'm going to choose to divide by. And that leaves me with b minus 3 equals b times this long, nasty number. Now, I'm going to leave the option up to you. If you would like to write the long, nasty number, you certainly can. If you want to leave it as log of 5 over log of 11 for now, that's perfectly fine. I'm going to write the long, nasty number here. So log of 5, close parentheses, divided by log of 11, close parentheses. And I get 0.6712. But I'm going to keep that number into my calculator because I still have a little work to do with it. I need to get these b by itself, I need to get these b's together. I have 1b over here, and I have 0.6712 b's on this side, because that's really what this multiplication is saying. It's saying 1b minus 3 equals 0.6712 b's. So if I want to get them together, I need to subtract 1b from both sides. So here's that long, nasty number, minus 1b gives me that negative 3 equals negative 0.3288b. You treat this just as if it was a normal number. If it had said 6b in front and you subtracted 1b, you'd be left with negative 3 equals 5b. Instead, it's just a long, nasty number that we used our calculator to calculate it. Now I need to divide by that long number. So on my calculator, I have negative 3 divided by second answer, because I want that calculator to input that entire number into here, not just this number. This will not give you a correct answer. You will have serious rounding issues. So my final answer is that b equals 9.1237. One more small thing to do in 6.7, and that's using the change of base formula. You actually have been proving / using the change of base formula throughout all 4 of these last problems. I'm just going to give you the formula now. Change of base formula looks like this. If I have log base b of a, I can rewrite this using using common logs. logs with a base of 10 so that I could use my calculator. And I do that by putting a log on top and a log on bottom. And I have the A and the B. How I like to think of these as basement and attic. The base is in the basement and the A is on top. And where do you find an attic in the house? On top. What that allows me to do is it allows me to take any log, even if I don't know that it's a nice, pretty number, and I can calculate it using my calculator. So this one, I have no idea what exponent I would need to raise 3 to get to 7. 3 to the something equals 7. I have no idea because I only know 3 squared is 9 and 3 to the first is 3, but 3 to the something equals 7? I have no clue. I'm going to let my calculator figure that out because it's not a nice number. It's irrational. The basement number is the 3. The attic number is the 7. So I'm going to rewrite this as log of 7 over log of 3. That's what it looks like in terms of common logs. Now I can let my calculator calculate that. Log of 7, close parentheses, divided by log of 3. 1.7712. Let's do it a couple more times. Basement number is 4, log 4. Attic number is 23, log 23. Basement number is 9, log 9. Attic number is 13, log 13. Basement number is 2, log of 2. Attic number is 5, log of 5. Now it's just a matter of me typing it into my calculator. Log 23 divided by log of 4. 4 decimal places, 0.8198. Log of 13 divided by log of 9, 4 decimal places, 1.1674. Last one, log of 5 divided by log of 2, 4 decimal places, 2.3219.